Right. Hope you are in the right room. Let's start with why C. Well, you want to program a microwave oven or a smart light bulb, C might be the language, or a pacemaker, some fancy braking systems in a car. If you want to develop a programming language or work on an operating system, supercomputing, guidance systems that goes into space, and maybe you just want the battery to last the whole summer. There are plenty of uses, places where you would like to use C. So my name is Olve Maudal. I'm here to give a reintroduction to C. I did last year at NDC Techtown. I was teaching a 2-day introductory course in C. But I also did a 60-minute session called 42 Silly Ways to Say Hello in C. And while working on that talk, I realized how much you can actually teach by using simplified examples and skip kind of the boring details and just go directly into the meat. So I challenged myself to try to cram as much as possible of the essential stuff into 1-hour presentation like this. So what you're seeing now is the premiere. It was finished around 3 o'clock last night, but I have been thinking about it for a year, so it's not rushed in any way, but the slides will be rushed because I have 259 of them. So let's start with a very proper and educational example. Notice how we are checking the return value from puts, and then accordingly communicate success or failure back to the runtime environment. And when we compile and run this code, of course, we will get hello. So this is your stuff, and the header files on the top of your program in your translation unit, they are basically expanded textually by the preprocessor. And here I extract significant details from these 2 libraries. And the first we see here are the macros, and they are textually substituted into your code. And here we see a so-called declaration or a prototype, which is saying that there is a function somewhere, I don't know where, but it exists. And the symbol, the linker, you can try to find that symbol and link into this program when you compile and link this snippet. And in this case, the function is part of the standard library. The external keyword is implicit, so it's usually skipped. And let's just rewind a few slides back to here and notice that, of course, there are other library functions you can use as well. Printf, which returns also an integer, but it returns some different values. Instead of just saying yes or no, whether it succeeded, it will return the number of characters it printed out. And this might lead you into something like this. You want to be really, really secure and kind of check that, yeah, really printing 6 characters. And there are applications where you need to check everything in C. But it's very easy to be taken down into a rabbit hole. You get more kind of checking code than actually functionality. And C has a limited and very weak error handling system. And that is one of the reasons why you probably want to consider other programming languages if you can. But as I said initially, there are places where C is still the dominant language. You can even get into the bizarre examples like this. This is inspired by some code that I found on a very serious website about C programming. But it's it's kind of ridiculous because we are checking the return code from printf and doing all the work, but we don't check the return code from fprintf and other stuff. So it's just, it looks like it's very serious and safe, but it isn't. And when it comes to C programming, you often have to just make a decision that something is just working. And if you are on a kind of a desktop computer running Linux or something like that, you probably can, it's a fair assumption to say that standard out is always working, at least for kind of snippets and toy examples like I'm doing here. So I claim that this is a decent way of saying hello, and I even go further. I go to this, where I remove the return, because since C99, that's 24 years ago, C has guaranteed that if you drop out of main, you will get whatever the operating system, the runtime environment expects for a success. So you will basically get exit success. This is the same as what C++ does. And then you're not forced to lie. You're not forced to say, yeah, success. You can silently drop out and get the default behavior. So this would be a good start. Now, you might find it a bit inconsistent that main says it's returning an int and it doesn't. But you just have to deal with it. There are plenty of them in C, and if that is problematic, then maybe C is not your language. Right. Hello. Oh, where is my hello? Oh, it's freezing. I need to start this one again. Ah, hello. There it is. All right, now to something completely different. Here we have some integers variables, also called integer objects of automatic storage duration. And we initialize them with a collection of constants: hexadecimal, decimal, octal, character construct, and escape sequence. In the standard library, the putchar function that writes to standard out, or more precisely, the passed-in argument is converted to a signed integer type before they are passed into the putchar function, and where they will be converted to an unsigned char before they are sent to standard out. And then putchar will convert that unsigned char back to an integer and returning back to the caller. And IOR error is reporting by an end of file constant. And this results, of course, in another hello. We talked a lot about conversions, some about conversions already. There will be much more. Here we have a suite of unsigned integer variables, wide ones down to narrow ones, typically. And they are all silently converted to a signed int before being passed into putchar. This is absolutely how C is supposed to work, silently converting between types, not giving any warnings. You can probably turn on some very strange optional flags, but if you put on vol and extra and all of those kind of things, you will not get a warning about narrowing of variables and widening of integers. And also, as you notice in the comments here, the only thing we have guaranteed about is a minimum size of these variables. It doesn't say anything about the maximum size. It is possible, and I've heard about computers that where everything is an int, where everything is 32-bit, but not, of course, the long, which is 64-bit. Even the char is 64-bit, no, 32-bit, and so on. And talking about conversions, also these signed, the unsigned integers, they have a signed counterpart. The signed is implicit, and the int keyword can be dropped. So very often you will see them like this. They are also being converted into unsigned int before passed to char. Without going into further details about it, but interesting that all the others, they have a signed and unsigned part. The char actually are three different types. You have the unsigned char and the signed char. They can be used for small integers, small numbers. And the char is a separate type that is ideal for, well, drum roll characters. Yeah, that's all. The conversion mayhem doesn't stop here. Watch closely now. All of these variables will also silently be converted to a signed int before they are passed into char. And once again, it's a feature. That's how C works. And C is a typical weak type. It's a statically typed language, but it's also a weak typed language. C++ is trying to make it a bit stronger, but C++ is also a weakly typed language. All right, now for something completely different. Here I created an array of integers and print them out to stand it out in the regular way. Now let's look into the details here. Before we do that, the extern keyword, well, we know that one. It's saying that the char is defined somewhere else. The static keyword is kind of doing the opposite. It's basically saying to the compiler, don't make this object available for anyone else to use an extern and say they can find the symbol here. So the A, by using static in front there, the A symbol will not be visible from another compilation unit, translation unit, an object file that wants to link with this program. Here we are now going to do a lot of pointer work. So here we are, first of all, the array is, as soon as you start using it in an expression, it decays into a pointer. So what we're looking at here is that A has decayed into a pointer that we are now dereferencing with the indirection operator. And we get an H coming out here. Here we are using the subscript operator, array subscript operator, which is basically just a syntactical, convenient way of writing what you see here now, where you take the base address +2, and then you dereference it to get the L out. Now, since addition is commutative, this also works, of course, 3 + A. And yeah, probably, I guess, the next step, very useful for pub quiz questions. But this is perfectly fine. There isn't much use for this construct, but I've seen it used successfully a couple of times. One was in an audio codec where there was this kind of clever way of looking up which codec to use. It wasn't necessary, but it kind of looked okay. But you can also sometimes find them in macros that triggers compilation errors if you are using the incorrect type passed into the macro. And finally, I show an example where we take kind of the address of the third element, add another 3 to that, and then dereference it. And we will continue with some pointer gymnastics. So here is what we're doing here is basically to take the address of this phantom element that is one beyond the array. This is a very common technique. Everything in C++ is based on this when it comes to ranges and iterators and so on. But it's also something that we do in C all the time. And there is a guarantee in the standard. It's always possible to compute the address of the one beyond element in a sequence like this. And then by doing that, we can refer to the other elements relatively. So in this case, the -6 element from the one beyond, -5, -4, -3. And here we are taking the pointer of the -2 and then dereferencing it, and it gets even worse, like the last thing here. Of course, you wouldn't write this yourself. But when you are using macros, or when you are looking at code generated automatically for you, you sometimes get these kind of constructs, and it's useful to understand what they are doing. And the answer is basically that these two, the dereference and the address operator, or the indirection, and the address operator, they are canceling each other out. So what you're looking at here is basically only this thing. Right. Now to something completely different. So here I'm repeatedly using the pre-increment operator to increase the index so that we can print out all the elements in the array. Notice that I'm using SizeT. It is possible to use an int, but it will usually take you in the wrong direction. An int is, first of all, int is a signed type. You probably want to use an unsigned type to index into an array, unless you are going negative in the array. But also the size, the width of the type you want to use to index into an array is machine dependent and runtime dependent. So it's better to include studef, and then you will get type def for SizeT that will typically give you an unsigned int or an unsigned long or an unsigned long, depending on what your machine you are running on. And it solves a lot of portability issues. So if you have had problems porting between 32-bit and 64-bit, this might be one of the things you have been struggling with in your code. But SizeT is your friend. There is also an SizeT, which can give you a signed version of SizeT. So, how are we going to deal with this repetition? Any guesses? Loop, yeah, of course, let's go for it. And yeah, GoTo can do the job. GoTo exists in the language of C. I had to show it somewhere. But also, if you look in the, for example, in the Linux kernel, source code for the Linux kernel, which is, by the way, one of the best sources for learning C. Beautiful, beautiful, beautiful code there. You will find plenty of users of GoTo. GoTo is used all the time. It's usually not used like this, though. It's mostly used to jump forward to clean up things. But you can also find examples where you look at it and say, this seems to express the ID best, and why not use it? I'm not encouraging anyone to start using GoTo massively, but it's nice to know it exists in the language. The key reason why I show it here is to give a build-up onto the other ways of iterating to it. One of the key kind of inventions or concept features that C introduced back in the early 70s was something called the compound statement. So here again is referring to putchar, because that's the one statement. But here the again label is bound to the compound statement. We have grouped statements together. And in C, nearly everywhere you can use a single statement. You can always put a compound statement instead by grouping them together with the color braces like this. Now let's fix the indentation a bit. And now you might recognize there is something similar, something that I recognized here. Yes, it's the do-while loop. So this is the transition into the do-while loop. And there is also a while loop where we put a loop invariant on top. And now we recognize a pattern that happens so often that there is a separate keyword and a loop construct in C and lots of other languages. And it works like this. So the for statement, the middle part of that one is the loop condition, same as the while is using. And now I have just left some open holes where we are now going to fill with the initialization of the loop variable and with the update statement, like this. And the for loop I show you now and the while loop we had earlier, they are exactly the same. They will probably produce exactly the same machine code. Well, I'm quite sure they will produce the same machine code. They are equivalent. Here we have hard-coded 6 elements. But it is possible to compute the size of an array, and this is an idiomatic way of doing it, where we take the size of the whole array and then divide it by the size of the first element, and that will give you the number of elements inside. So in this case, we can now change the size of the array, and the loop will still work. The compiler knows how to count, so you don't have to specify the size like this. You can leave it blank, and then the compiler will say, yeah, there are 6 initialization elements here, so therefore I will create an array of 6 integers in this case. There are some useful functionality in the main now, so let's extract it into a function. Like this. myPutChars. That takes a base pointer and the number of elements, and then use the traditional way of looping through every element from the beginning to the end. And you can see down here that we are passing in this one. Now A is used as in an expression because this is evaluated as an expression, so it will decay to a pointer, and that is what we are passing in here. And N is passed in there. Inside this function, there is another way of iterating. Some people call it iterator pattern. Very much used in C++. And that is, instead of having a base pointer and then index into each element, we compute the beginning of the sequence, a pointer to the beginning, and then we compute the address to the phantom element, the one beyond. And in the loop now, we are basically starting with the pointer to the beginning. And as long as the pointer, the iterator pointer, is not the same as the end, we are doing this loop over and over and over again. And it's of course used in C as well, and has been used from the very beginning of C. But it's everything in C++ is basically iterating like this, ranges and so on. So inspired by C++, you might say, but it's a useful way to think about iteration as well. Now, these begin and end, of course, they can be passed in as arguments like this. So now the caller basically sends in the base pointer to the base, and then the pointer to the one beyond. Okay. All right, but now instead of giving the beginning and the end or the number of elements, we might introduce a convention that says if there is a 0 in the end of the array, then you should stop iteration. And we can now change this loop condition so that we dereference the iterator and check that it's not 0. As long as it's not 0, we are just iterating over and over. Now, this is the same as this, and we like terse, concise, small code. So it's often written like this. And now we don't need the end pointer anymore. We can just pass in the base of the array, and it will loop until the 0 element in this array. And now we can get rid of the size calculation as well, like this. Now, here we pass in the beginning and we create an iterator. So why not just take it in as an iterator? And similarly, here we're using the pre-increment, which you should always default to the pre-increment. For some reason, C programmers tend to default to the post-increment. I think we should do some work on convincing to by default use the pre-increment. But this is a particular case where if you put the post increments here, we don't need the update in the for loop anymore. And now we are recognizing that this is basically a while loop. And it's probably time to reveal what these numbers are. So I change it to a char, and then I use kind of a constant literal instead. Oh, sorry, character literals instead. And what you're looking at now is exactly the same as this. So the string representation is basically a nice way of saying exactly this. It's just more compact than all the braces and all the commas and so on. And implicitly, you will get a 0 in the end always when you use the string literal like this. Now, if we continue to make it more and more similar to puts, we just add a new line in the end, so we don't need to have it in our string literal. And then we can change it to my puts. And if we also now change the it to the more common s, which is often used in Koenig and Ritchie and the library and so on, we realize that we have basically created puts, but without returning an error condition. And of course, we can put the literal inside the call, and let's just go for puts anyway, and we can get rid of this one, and we have a nice hello. Oh, before that, yes, we have an include that we don't need. We have had it for a few slides. Remember to clean up your code, get rid of the unnecessary includes. It's quite common when you look at really large code bases that half of the compilation time is actually opening and closing files to be included. So a very good advice for anyone working with a large code base is to look at how you can get rid of unnecessary includes and how you can avoid header files to be included over and over and over and over again. And there is something called an include macro guard that you can use to avoid that, and so on. Also, pragma ones is sometimes used. But anyway, let's clean up, and we have a nice hello again. All right. Now to something completely different. I like cooking, and I take it seriously. I'm not very good at it, but I still take it seriously. And here are some notes I made while doing a 1.3 kilo steak in the oven at 125 Celsius. So I just use them as an excuse for creating a structure with a time, temp, and scale, because sometimes I accidentally hit the button on the stekethermometer, and I end up with Fahrenheit instead of Celsius, and I have to fix that. But in this example, I just let the Fahrenheit be here. So when you run this code, here is the structure. Here is an array of these structures initialized, and when here I compute the number of samples, observations, and here I just have a pretty print of the time, the temp, and the scale. And this is the output of this program. I need the screen state here, so I just put them on one line, even though I don't do that in practice, but I just need more lines on the slide here. So looking at this loop here, this is just an excuse for showing two constructs, continue and break. And suppose that if the scale is not Celsius, then I don't care about it. So I say continue, and that means go back and do the next operation, the next iteration. Similarly, if the time is more than 131, that's 2 hours and 11 minutes. I took the stake out. There are still observations, but I don't care about them. You might say, let's just break the iteration. I'm not interested anymore. So this was just an excuse to show continue and break. But there is a warning here, though. Continue and break. Well, continue in particular, they are like bug attractors. Very often when you have bug in the code, it's close to a continue. Used in the most simple scenarios like this, it's probably fine. But in your code base, you should probably do a search for continue and read the code around it, and you have a high chance of finding a bug, because it breaks the logic, it breaks the thinking, both for the computer and for the compiler, no, for the programmer, and it's often a good idea to be careful about using continue. Used like this, I think it's fine, but more complicated examples are often not fine. They can be solved in different ways. Yeah. So this is the output we get when we have done the continue and break. Now I need to rewind a bit, simplify the slides to fit more into them. So I'm simplifying this back to what we had. I'm also just getting rid of a few observations to get a few more lines to work with. Sometimes when I do these observations, I get them in the wrong order. I might write them on a different note and so on. So here, just to illustrate that, I swap these two observations. So they are not in timely order. Of course, I could have sorted them and do all of that kind of stuff. But now it's a nice chance to show this one. And this doesn't exist in C++. Well, maybe it came in C++ 20. You can do this. You can specify which element you want to initialize in the sequence, in the array. And you can also use these names to say, these are the elements I want to initialize. And you can swap the order and things like that. Sometimes this is super convenient. This is called designators, and they provide explicit initialization in a list like this. Designating initializers. Yeah. All right. Slightly changing. We are still working with the temperature here, but not with an array. We are now introducing a compound literal. So here I'm basically creating an object as I'm passing it into the print sample function. And the print sample function is taking a copy of that object that we can work with inside of the function. This might, I've seen examples or heard about examples of using this as kind of a poor man kind of named arguments way of passing named arguments into a function. I'm not sure how far you should go down into that route, but I guess you see that it's a possibility of doing so. All right, so this will print out a temperature. Now, we might, instead of passing a copy of the whole structure, we might want to just pass a pointer to that structure. By the way, in C, you can only pass by copy. There is no such thing as pass by reference. And even pointers are passed by copy because they are pointers that you are actually passing. So you might pretend like it's something more advanced, but it's still a pass by copy. So this is also a pass by copy. We are copying in the pointer to this object. In this case, it won't save us much performance. Actually, it might be much worse. But it's quite common to work on pointers instead of big structures that we are copying back and forth into functions in C. Notice that since we are passing a pointer, we need to dereference the pointer before we can access the element inside of the structure. So that's what we are doing here. Now this has a nice syntactical helper with this arrow operator, also called the structure point operator. But it's useful to know that what you're looking at here is the same as we see here. Since we are not modifying the object that we are receiving, you probably want to put a const in front. And const is just as important in C as it is in C++. So whenever you're working where you have a pointer to an object and you do not intend to change it, you probably want to declare it as const. It's a very strong communication tool to other programmers and yourself and the compiler that this is, you're sending in some data, but you're not giving away the ownership to it. And you're not allowing modification on the data. And here I call it print sample. Print sample is a perfectly fine function name for this, but it's quite common to see this naming standard or whatever, where the first part of the function is basically the structure name, and the last part is kind of the member function accessing and using that structure. And by doing this, you get some kind of feeling that we can do some object-oriented stuff. I would say that you can't really do that. I have seen so many efforts of trying to do object orientation in C. And when I see the horrors of the result, I always recommend, why not use C++ instead? If you want to go deep down in the object-oriented way, C++ is probably your language instead. But anyway, it's very common to see something like this. And you can take this idea further. So here I've implemented not a command member function, but a query member function, where you pass in the temp pointer to a temp sample structure, and then you query, can I get the temperature in Celsius, please? And inside here, you're computing, doing what is needed to always return the Celsius version of the temperature in that observation. This gave me a chance to show the if and the else if and so on. But what I really wanted to show was this. This would be a typical example where we would use switch and case. The switch must be, well, typically it's a numerical value that you can then make a decision, should I go to this case, or these cases. Notice that Here we have a fall through from R to K. And I claim that this is a perfect example and why switch is so nice. You really want that fall through. And it's so obvious that you probably don't want to document it with this kind of poor man annotation. By the way, this annotation is formally defined in the C23 standard. Then it comes with square brackets and so on. But you get fall through. But beware that every case that you don't want to fall through on, of course, you need the brake. And I realize now you probably need you want the brake here as well on the default, just for consistency in case you decide that the default should be a case instead of the default and so on. I don't know. All right, I got the chance to show the switch and case. Before moving on, here we are using a character to hold the scale, whether it's Celsius, Fahrenheit, Rankine, or Kelvin. But you could also introduce an enum with a temperature scale. It's a very primitive mechanism. The enum in C mostly is a bit like creating just constant. You can wrap the enum inside of a type, no, inside of a struct, and somehow emulate the enums that are type safe and so on. It takes you a bit in the right direction, but not all the way. It's a primitive mechanism, but it's very useful. And for example, this is a decent example of using enums. In C, enums are usually stored as an integer. Maybe that's defined in the standard. In C++, the standard says just the number of bits required to store the enum, which is usually, if you have less than 256 cases, it's usually a byte or a char. Sorry, a char. All right, now to something completely different. So here I want to talk about storage duration, memory, and how we deal with that. What you are looking at now is we are creating a sample, which is a so-called object of automatic storage duration. Some people call it a function variable or a stack variable. I don't like those names, especially not the last one, stack variable, because it kind of implies that C has a stack. And theoretically it does. But in practice, the compiler will try to avoid using a stack as much as possible. So if you're looking for a stack inside of the produced machine code, you will often not find a stack in C. And in the C standard, the word stack is never mentioned in the standard. It's a long word, automatic storage duration, but it's a useful word to use because if you search on the internet and you have questions about it, if you search for stack variable, you will get to thousands and thousands of recommendations for how to do things written by people that don't understand much about C. If you search for automatic storage duration, you won't get that many hits, but they are probably of a higher quality than kind of the stack variable people. The scope is also interesting here. The scope of sample is within this function demo. Of course, try to avoid using global scope. We often want to limit the scope of our symbols as much as possible. That's also the reason why we tend to put static in front of things to limit the kind of linker visibility. Where can this symbol be seen? And the same is true here. It's the scope of sample it's not visible outside of this function. Now, if I take this object of automatic storage duration and then move it out into the file level, I get an object of static storage duration. So every object defined in the file, on the file level, they are by default implicitly static. So adding static in front, it's the same keyword. And to my surprise, it is actually in the standard, it is called the storage specifier, also when used like this. But it's an overloading both of the keyword and intention of it, because as you know, we talked about, what it's doing is reducing the linker visibility. Other object files cannot see the sample now that you have static in front. All right, let's move it back into the function, but now using the static keyword. Here, static means something else. Now, static means that the object, well, I forgot to say that. Let's go back. The object of automatic storage duration starts to exist on the beginning of the function, and it is destroyed when you go out of the function. Well, it isn't destroyed as such. It's not valid anymore. So if you reference into it, you get undefined behavior. So in practice, it doesn't exist. However, if you put it, objects of static storage duration like this, they are created before main, and they stop existing after main is finished. And the same is true also if you put them inside of this function. So the object is now created before main and allocated and ready before main, and certainly before you come to demo, and it will exist until the program terminates. This also means you can return a pointer to it. So here I'm taking the address of this object of static storage duration and return it back to main so that main can print out the sample. And this is about dealing with the ownership and so on. I'm not saying that this is necessarily a good idea, but it's not necessarily a bad idea either. It's something that you can do because the object exists. It has static storage duration, exists from the beginning to the end of the program. Or storage for that object exists. Now, the obvious next thing to show is using malloc, which is an object of, correct me, allocated storage duration. Dynamic storage duration, yes. Yeah, but I think this is in C, it's a dynamic storage duration, but this needs to be checked. But anyway, malloc. So malloc is a way to ask, usually the heap, even though that doesn't exist either in the theory, in practice it does. So it asks for some memory in the free store, and it will return a pointer to it if it succeeds, or null if it doesn't exceed. And if you can't get memory to work with, you probably don't want to continue your program. So exit failure might be what you want to do, or somehow violently scream, I'm not ready to continue. You certainly don't want to ignore it, because writing into a memory location that you were not given, or null, for example, it's a terrible idea. Don't do it. And now, since we have an object of dynamic storage duration, we can do whatever we want. It will exist until we release it with a free. So you can choose to do it in the same place, or you can create it one place and then say, well, I will delete it later, and so on. This is perfectly fine. It's something that we often do with dynamically allocated memory. But of course, you might want, I would like to show an example where we do the malloc and the free in the same function. So I'm moving it in here now. Malloc is there, free is there. and I'm printing out the sample, and it gives me a chance to show the more typical use of a GoTo. It very often looks like this. So you have some cleanup section in your function, and then if you get some errors after having grabbed some resources and allocated some memory, you go to the cleanup section and you get rid of your stuff. Now, this can always be solved with an extra layer of indirection. So it is a choice you have whether you want to use GoTo like this or not. But sometimes you're in a situation where you don't write all the code yourself. Sometimes you just have to deal with code written by others. And then it's useful to understand this particular idiom. I think I counted more than 100 uses of this in the Linux kernel. It's a very common way of doing it there, for example. Layer. Layer. Yeah, and yeah, you can also layer them, yeah. All right. We are doing nice on time here. We need to talk about memory a bit. On my development PC, the one I'm writing my slides on, often I work in an embedded domain, and then this isn't true at all. But on kind of a desktop computer, and on my PowerPoint generating machine, I get, if I run this program, my ints are 4 in size. My double is 8. Char is 1. That is actually the only value that you know is always 1. The others, they can vary. They can be, the integer can be 4, it can be 8, it can be 2, it can be 1. Someone wants to correct me? Yeah, 1. It will probably be 1 if the char is 1. No, if the char is 32-bit. Then the integer can be 1. So theoretically, you don't know how big it is. But then you might be a bit surprised by the size of the structure. It's 24. And to encourage some interaction, anyone would like to suggest why? Yeah, all right, you. Sorry. Yes, it's alignment. And I like that you said alignment first. You said padding. Because it's not because of the padding that we get it. It's because of the alignment that we get this, this size. And the thing is that stuff like double and int, they often want a certain alignment. And on my machine, if the compiler puts a double onto an address that is not divisible by 8, I get the program crashes. It's often a segmentation fault or something like that that it ends up with. Similarly, if the int is put on an address that is not divisible by 4, it crashes. The char is the only one on my machine that you can put anywhere you want. So these structures, they come with an alignment requirement. And the rule of thumb is approximately like this. The alignment requirement of a struct will typically be the same as the align requirement of the strictest element inside, which in this case is 8. 24 is divisible by 8. So that's the reason why we get 24. And then the compiler will do what it takes to kind of pad up the others so that they are correctly put in place. Yeah, I removed that slide, but there is actually a keyword in C called align off, where you can ask the object and the type, what is your alignment requirement? Yeah. On my machine, that's correct. Yes. So What the gentleman over here said is that if you change the order of this particular structure on my machine, which is probably very similar to yours, since you knew that, then the int, which has an alignment requirement of 4, the char can be wherever, so that it can take one of the otherwise padded spaces, and then the double will get an aligned 8 mod 8 address position, and then the whole struct will get an alignment requirement of 16. Well, of 8, it's still alignment requirement of 8, but the size will be 16 on my development, my PowerPoint generating machine. On embedded, it's completely different. You have to study the ABI, abstract binary interface, that tells you about the alignment requirement. All right, and then the final example. And I have shown this many times in talks before, so some of you might be like, oh, not again. But if you haven't seen it before, you might enjoy or be scared to death by this one. This is a piece of code that is, of course, it's rubbish. But you can type it into Java or into C# or a lot of other program languages, and it will always generate exactly the same result. It's well defined in many other languages, but not so in C, not so in C++. Spend a few seconds, just look at it, try to figure out what do you think it might be. On my machine, well, you can give, or you can, what would it be on your machine or your kind of chip when you are doing some embedded development and so on. And I take anyone that would like to suggest? We will maybe come back to that, yeah. All right, who wants to make a first guess? Yes, thank you. 13, I love that answer. Anyone else? 0, I love that answer as well. Come on. Any higher, lower? Well, the point here is, and this is super important, and it's true in C++, it's true in C, and that is the evaluation order is mostly unspecified. We don't know, we cannot know whether it's trying to evaluate expressions from left to right. If it's a strictly left to right, I think you get 11. If you do a strictly right to left, you get something else. If you do kind of a spiral evaluation, you get something else. But what compilers often do is that say, I don't care because this is a sequence point violation. You are not allowed to update a variable twice within a sequence point. And that's, the sequence points are basically the rhythms in the program that says when do these evaluations have to be stored into some place so that it can be used for other evaluations later. In more modern standards, it's called sequence before and sequence after and so on, but the rules are approximately the same. So since we don't know the evaluation order, if we evaluate this one first and then this one and this one, we get one result. If we evaluate this one first and then this one and this one, we get another result. And here are 3 compilers. The GCC compiler will give you 12. The Intel compiler will give you 13. And Clang will give you 11. No, on average they are. Well, they are all wrong. So by that, thank you very much. That was my talk. We have room for a couple of questions or comments or whatever, if there are. No? Or I will hang around here, and you can discuss this anytime. And I plan to publish these slides. I just need to put on some talking bubbles and so on, so that it's possible to read them without the narration of me. And I will also add a few extra things there, because then I'm not limited to 60 minutes. Then I can do maybe 90 minutes when I present the slides. Yeah, there is one question over there. I will repeat the question. Oh, yes, go for it.
Is it possible to find out the maximum value of a SizeT typed variable?
Yeah, it's in limits.age. You can find the limits of the types. So just as you can find the biggest ints or the biggest unsigned longs and so on, I'm quite sure you can find the maximum size of SizeT as well. Yeah. Any other? Jørgen over here, yeah. Microphone. Yeah, but it needs to be on the recording.
Right. So doesn't C++ from 17 specify the evaluation order of operators? Which would sequence this, right?
I'm quite sure it didn't make it into 17.
Might have been.
Because then I think I would have known.
Okay.
I followed C++ until 17, right. And now I don't follow it very closely anymore. But they are working actively on the evaluation order. I'm not sure if they do it on the expressions, if that is their intention, like this. But they are certainly doing it on the evaluation order on the function arguments and so on. So typically, GCC will go backwards on the function arguments. Arguments you pass into a function will typically be evaluated from right to left on GCC and left to right on other compilers, and some just do it in a random order. Yeah. But the evaluation order is one of the sources of a lot of kind of interesting behavior in C and C++. Yeah. All right, enjoy the conference, and yeah, that was it. Thanks.